Okay. Hello, everybody. Nice to see you. My name is Alfred. I'm the CTO of IncludeOS. Today I'm going to deconstruct the operating system. Actually, I'm going to build or show you how to build a tiny little operating system from the bottom up. So if you're not familiar with IncludeOS, how many knows about IncludeOS from before? Okay, good. How many knows about unikernels? Yeah. So IncludeOS is a zero overhead library operating system, and is written from scratch in modern C++. If you add single address space to that definition, you'll fulfill the requirements for a unikernel. So when it's a single address space operating system, that kind of implies that it's also a single process. So we're making a library operating system designed to make your ELF binary bootable and completely self-contained. So I want to repeat this fact. There's 0% Linux inside. We've given talks about IncludeOS, and we've told people that it's written from scratch in C++. Still, after an hour, people raise their hands and ask, but there is Linux inside, right? No, there is no Linux inside. It's all C++. So I'm going to start with a question. This is a real Stack Overflow question from 2015. How to boot my simple HelloWorld program? Suppose I have a simple HelloWorld program which is built in C. Now, how can I boot it during start my PC? Okay, never mind the syntax. Is it a fair question? How many thinks it's a fair question? If you were a moderator on Stack Overflow, would you allow this question? Not many of you. Who would deny this question? Who would say it's not an okay question? None of you. Well, the people of Stack Overflow didn't think it was a fair question. It got downvoted. It was closed as too broad. People were actually quite rude with this guy. So this guy is saying, sorry to burst your bubble here. The very fact that you ask how to do it means you don't have a deep enough understanding of computer science to be able to do it. That's pretty rude. But where does this come from? Where does this idea that it's so hard to boot an HelloWorld program, where does it come from? It comes from the fact that on your computers you have these huge operating systems and you're used to the fact that, that's just how it is. But it doesn't have to. So let's go back in time a little. There used to be a time when users were in control of their computers. Are you guys in control of your computers? You're programmers, right? I don't feel I'm in control of this computer. I think Apple is, to be honest. I see these updates. I don't know what's going on. I say, okay, well, they do something to my computer. It's probably fine. But, as a systems programmer and as a C++ programmer, I like to be able to control my own computing. That's also a famous statement from somebody else. Let's not go there. But I like to be able to control my computer. So let's look at an ad. This is an ad for an IBM personal computer. Because the guy wanted to know how he could boot his HelloWorld program on a PC. So, here's a PC. This is an IBM personal computer XT. Okay, so it's not the original IBM PC. It's the extended version where you got a hard drive. Right? So it's slightly more sophisticated. So IBM sold these first PCs with 16 to 64 kilobytes of memory. Would it have been a fair question back then? I'm absolutely certain that the operating systems that were popular at the time, I think Microsoft DOS was probably on this one. It was a tiny, tiny, tiny thing compared to what you have on your systems today. So I think maybe the fact that machines have become so large, that could be a contributing factor. But I think the fact that you want to run so many things at the same time is kind of the main factor for why operating systems are very complex these days. So let's deconstruct. Let's try to make the smallest possible operating system for running HelloWorld. I know it's probably not an interesting example, but it kind of is, and we'll get somewhere more interesting later. So I'd like to start here. This is what happens when you start your computer with an empty hard drive. Okay? And this is actually how IncludeOS started. I was doing research into cloud computing, and I was interested in virtual machines. I wanted to run thousands, or actually, if I could, I would like to run millions of virtual machines to do interesting research on cloud computing. So I thought, actually HelloWorld is quite a good place to start, to figure out, what is it that makes these virtual machines large? And how can we make them smaller? So I'd like to answer this question, and I'd like to answer it in the spirit of Bjarne Stroustrup's zero overhead principle. Now, why should we listen to Bjarne Stroustrup? Well, he actually just won a medal, right? Yeah? Did you guys win medals? I didn't win any medals. So I'm inclined to listen to this guy. So let's try to boot your service and to apply this zero overhead principle and not pay for what you don't need, right? Is it possible? Yes, it's possible. This is a bootable HelloWorld program. If you're interested in x86 assembly code, you might want to study this. I'm not going to go into the details. It's about 30 lines, so that wasn't so hard, right? I booted HelloWorld. Well, I wrote HelloWorld, and this is how you boot it. It's 2 lines to assemble and then use, in this case, a virtualization tool like QEMU. That's a hypervisor. That's something you can use on Linux or Mac. You could also boot this on VirtualBox, or you could boot it on your physical PC. So this is what happens. Hello World. So did I just boot Hello World? Yes. This will also work on hardware. So I would say I booted it on a PC. Oh, but these guys don't agree. They're actually gathering angrily outside town hall, demonstrating, pointing out what's wrong with this example. First of all, it's not C, right? He specified that he wanted to boot his C Hello World program. Okay, so I gave him an assembly version. That's not quite good enough. 16 bits, yes, well caught. It's a 16-bit instruction set you're using when you're starting. So, and also, one guy noticed that this is not a generalizable solution. Inside of that first boot sector will only fit 512 bytes. It's okay for Hello World, but you can't do much else. Well, you can do a lot more, but it's not completely generalizable. So, oh, this guy isn't angry, he's just determined. And, okay, so he's not happy with 2 lines, he wants 1 line. So, a one-liner to build and boot a Hello World program. That's something we've actually made, and we'll go through that. So first, let's address these issues. The fact that it's not C or C++, that could be easily alleviated. Obviously, the compiler is much better at writing assembly than I am, so it could probably, at least this for loop here, and the actual print statement could be much nicer, probably if you allow the compiler to just output this code. But there are some other problems. We are using some privileged instructions here. You can see that I'm saying CLI and halt at just above the arrow there. Those are privileged. Also at the bottom, I have this special statement to fill out the rest of the binary with zeros, so that in total it forms a 512-byte file. And at the very end, the last 2 bytes is supposed to be AA55. That's like the magical signature for the BIOS, and it sees those last 2 bytes, and then you're absolutely certain this has to be a high-quality bootloader, because those bytes are at the end, right? Okay, so the fact that it's 16 bits, is that a problem for Hello World? Maybe not. It's not very generalizable. Obviously, if you want to do something more interesting, like compute, do something cryptographical, or do something that require speed and performance, then you'd expect my system to be able to alleviate the full instruction set of the architecture. So let's consider this boot one-liner that we're trying to make here. We just want to say boot and then your program, right? So that statement has some interesting side effects, and we're going to look at some side effects of various things that pop up when we're trying to make an operating system, and we're going to try to address this zero overhead principle to those side effects or those questions. So obviously it was an assembly solution. He wanted a C solution, so we have to link with printf. That's part of the C standard library. Now printf isn't going to randomly start writing pixels on your screen, right? You're probably happy it won't, and it's not going to decide actually where that output is going. Printf is just a library function, and of course it needs a backend in terms of a system call. So we're going to have to implement that as well. In order to satisfy the guy who didn't like that we used 16 bits, we need to switch to 32 or 64-bit mode. We need to load an arbitrary sized C++ program, not just 512 bytes. So this becomes a generalizable solution. You probably also really quickly want us to initialize heap and stack, right? At least you want a sane stack so that you can use functions, call functions, have stack frames be created and destroyed without, for example, colliding with a heap. You also want a heap so that it's a safe area where you know that you can use malloc and friends, or you probably shouldn't use malloc and friends, but you should use more sophisticated C++ techniques for memory management. And then eventually you want me to jump to your program, and you also want me to kind of handle displaying that output on a screen. So the linker can take care of the linking part if I provide a statically compiled C library. And we do that, that's part of the bundle you get when you install IncludeOS. Now this part, let's try to implement it. How can we make the simplest possible backend for printf? So printf is part of a library, and of course this library will already have programmed into it calls to the operating system, and that's what we have to implement. So this is the set of system calls that new lib, it's a version of libc we're using. So this is the minimal set of system calls that you need to implement in order to run libc. So let's see what's needed for printf. I think you can get away with only write. There might be a call to is a tty for printf. It will check, is this a terminal or is it a file? Do I have to do some open first? But the one that's actually doing some I/O and actually doing something dangerous, that's the write statement. So let's make a backend. So this is a complete backend for printf. It's a minimal backend, but it's complete. And let's take a look. So first we have some abstractions around the in and out instructions. You can see I'm using some inline assembly here. That's because these are privileged instructions that the compiler isn't going to randomly just emit when you're building your program. The reason for that is that if you try to run these instructions on a normal user space Linux or Windows binary, what's going to happen? You'll get killed mercilessly, right? And we'll get to that part, but we need them for this exercise of making a driver. So we start by making some abstractions around those. Now we make a serial port driver. That's quite small, and this is one of the reasons why we like the serial port. It's the only peripheral that really doesn't need anything in terms of a driver. You can just start talking to that port, and it's going to work. You might need some initialization in advance. You can look at the comment there to see where in IncludeOS you can find this exact function. We have this. And then, on some systems, some platforms, there might be some initialization ahead, but it's really very straightforward. So it's a for loop. It's reading from the status register and it's checking that, is this serial port ready to receive data? And once it is ready, then you actually output the byte one by one. And then we can do our first system call. So we implement write. Let's ignore the first parameter for now and just see it's a pointer and a length. So we pass that on to the serial print statement, and that's it. Should probably be implemented a bit more carefully, but this is going to work. And now finally we can make our int main printf HelloWorld, which is something I expect is a reasonable answer to the original question on Stack Overflow. We have allowed you to use printf, that's normal C. We have implemented a backend for C, and we have also done the necessary things to bake this together into a binary. And we're going to look at some of the details of that. Oh, these guys are worried. How about kernel protection? Are you using blocking I/O? That's crazy. Isn't out privileged? Yeah, I mentioned that. We probably have to address it. So let's take a look. There are some tricky side effects. InB, that's inbyte, that's again using a privileged instruction. But the important part here is that this while loop is going to be blocking. Okay, so this is one way of communicating with devices. This is a way you could implement networking. You could have port I/O talk directly to the device using in and out ports. The problem with that is the CPU is going to be occupied 100% of the time. And of course, that's not very efficient. So another thing you have to deal with is privileged instructions, because they are supposed to trap. We'll get back to that, but it's also an interesting question, should we context switch here? Usually when you do system calls, I just called this a system call and nobody reacted, but usually what are system calls? They're not just function calls, are they? Are they just function calls? No, they're not. System calls usually trigger a context switch where your process is actually completely scheduled out, the kernel is scheduled in, and it's running in a different CPU protection level. And that's necessary in order to do these privileged instructions. So usually a system call isn't just a function call. So we should probably ask ourselves, well, is this correct? Because this works. So what's wrong? Is there something wrong here? Is there something important that I haven't implemented? So we could ask ourselves that question, should we do a context switch? Should we enter into a higher protection level? Or isn't that necessary? What's the zero overhead solution? So we've talked a little bit about the privilege and context switches. The important thing to point out is who are you protecting, who are you actually trying to protect, right? Because these sensitive instructions or privileged instructions, they are going to cause a trap, but only if you are in an unprivileged state. If the CPU is set to be in an unprivileged state, that's when it's going to cause a trap. If you are in ring 0, the default state and the most privileged state, is it going to cause a trap? No, of course not, because somebody at some point has to be able to actually talk to the devices, right? So I say that the zero overhead solution for some use cases, not all use cases, is to stay in ring 0. It's a surprising amount of things you can do there. So yes, you have a lot of privilege, but remember that the compiler isn't going to emit these privilege instructions at random, right? So if you write normal C++, it's going to emit non-privileged instructions, and that's going to be quite okay. So, but if you want to start doing these privileged instructions, you can, but that's not going to be writing normal C++. So port I/O versus direct memory access. Direct memory access is the usual way we do this, and I don't think we're going to have time to look into the details, but our network drivers are implemented in such a way so that we just use port I/O for signaling the physical device and then for initializing the physical device. We're not using it to transport data. Okay, so the physical network, the device is going to receive the packets off of the physical wire, it's going to put those packets up in my memory, and then it's going to interrupt me and tell me, now you have packets, right? So I don't have to spend a lot of CPU cycles just fetching all these packets. I'm just getting notified when they're already there. And the same thing goes in reverse. So for something that's even remotely performant, we have to use DMA. So I think that's the zero overhead solution in this case, but it might not be that simple and clear-cut all the time. So we make it platform dependent. We are bundling parts of IncludeOS into different bundles, and we're calling them platforms. And we have one platform called x86PC, and that contains all the components you need in order to talk to a modern x86 hardware platform with advanced interrupt controllers, advanced IOQ controllers, everything. But then we also have this x86 Nano. If you know that your program doesn't need any of that stuff, for example, we're making a chain loader, all it needs is to read a binary and jump to it. In that case, you might not want to go through the trouble of initializing all of that hardware. So let's get back to booting and let's reuse IncludeOS parts to get this C program booted. So the linker part is done. We implemented the syscall. So now you need a bootloader. We're not going to put this code inside the bootloader anymore, which is essentially what we did in the first example, but it only fits 512 bytes. So we're relying on a third-party bootloader, or you could use our very simplistic, rudimentary bootloader that we made to be able to do the smallest possible binaries. That's just a 512-byte bootloader that's going to lift your code up, put it up in memory, and then jump to it. So this bootloader is going to switch to 32-bit. We can bake in also, by default, we're going to also bake in the necessary assembler to the very beginning of your binary so that it will also switch into 64-bit so that you'll start in a kind of in the most modern x86 environment when you boot. So loading, that's taken care of by the bootloader. We also initialize heap stack and BSS, etc. We expect that you want this for something remotely more interesting than HelloWorld. So you can look at that code there, kernel start. That's where all that is. That's also the good place to start if you're interested in writing your own kernel. So we have all this tooling around to make it easy to boot and bake things in as a bootable binary, and this is where you start if you want to implement your own. And then display the output on the screen. We showed the original bootloader was actually writing bytes directly into video memory. So that's one way to get pixels on the screen. We also showed you how to do serial port, which is nicer if you're running in a virtual environment. You'll get the output as actual data out into your terminal. So here's your one-liner. We made this little tool. It's a Python script, and it's actually controlling QEMU. And we're going to work on improving that, but it's quite useful already. So if you have that code, just the code that I had in the previous slide, all the C code with the printf backend, etc., you put that in a file called service cpp, you say boot dot after having installed IncludeOS, then this is going to happen. Okay, so it's booted your HelloWorld C program and it did it in a one-liner. That was kind of the mission for this first project. So this is an overview of the tooling. We have libraries, we have your program, and it's going to, for example, if you say printf, then the linker is going to pull in what the printf function. The printf function again needs the backend, the system call, and that's located in the os.a library. So that's going to get pulled in. You can attach drivers for various platforms, and you can also embed a memory disk so that you have a file system, etc. in there. So with all that put together, you don't have to write your own backend for printf. You can actually just write a normal C++ HelloWorld program, and you can say, int main printf HelloWorld, and you can just say boot dot, and that's going to come up and do this. Slightly different output because we don't use the main signature by default, but we made it, made it into a weak symbol so that you can supply the main if that's what you prefer, and when main returns, what's left to do? I'm a single process operating system. I can't really do anything else. You're in charge. Your program exited, so I'm just reporting the exit status. These guys are rioting again. HelloWorld doesn't pay the rent. So what pays the rent? They want the web server. So they want me to show you how to boot a simple web server and how to implement the backend for a simple web server. Should we do that? Yeah. Just use HTTP, right? Not that hard. How hard can it be? I'm telling you that 90%, I think, of our efforts in IncludeOS has gone into making networking subsystem. It's not by any means trivial. We've done it, and it's actually working really well. But so I can't show you that in detail, but I'm going to at least address your questions. Okay. 0. That's quite a tall order, but we're getting there. We are there at the point where we can do this. So let's see if we can get help from the system calls. I want to write a HelloWorld web server. I have all these system calls. Maybe if I implement all of them, not just the right one, maybe I can get a web server. Do you think? I don't think. But let's take a look. So the green one, the S break, that means extend the memory assigned to this process. Actually just give it more space. That's actually the backend for malloc. So malloc is provided by the libc. It's just an algorithm for handing out buffers of different sizes. And then it uses a very simple syscall sbreak in order to provide that. So that's useful, certainly, and we need it, but it's not going to give us what we need. But this read syscall, that might be useful for actually reading off a socket. You could use it for reading off a socket, right? So maybe we can start using that. So this is a POSIX signature for the read function call or system call. So maybe that's a good starting point, or maybe it isn't. Is this how you would start in modern C++? If you were writing the backend for a web server, if you were writing that networking subsystem in C++, is this how you would start? Who would do that? Is it beautiful C++? Well, let's see. Well, if you read the specification, it's blocking by default. So that means one of two things. It's supposed to block, right? Because you're supposed to have continuous execution here. You're supposed to just say read how many bytes you want to read off of the TCP stream, which might not be open yet, who knows? But you're supposed to just say read, and it's going to sit there and wait until all those bytes are have been filled. There are async options to this call, but the default is to block. So I have a choice to either spin in a spinning loop, spending 100% CPU, or I could do a context switch, which is really costly. So I think this approach, just already here, I'm saying that doesn't sound like zero overhead. These context switches are costly. I have to implement some kind of threading and some kind of stack switches. I have multiple stacks that I have to juggle. That's a lot of stuff just to be able to print HelloWorld in a web server, right? And it might come in handy. It might be that we need to have full-on preemptive scheduling with all these context switches, but we don't need it yet, and we don't want to implement stuff until we actually know why we need it. This is another thing. I don't think this is natural C++ to have these integers that represent file descriptors. What is a file descriptor? I have no idea. What's behind this? It's just an integer. What's behind there? Is it a file? Is it a socket? Is it open? Is it closed? What is it? Magic. Yes, it's magic. Exactly. It's magic and it's opaque. So is this what I should start implementing? Should I make these file descriptors? It doesn't seem intuitive for me as a C++ developer. It does not seem intuitive at all to our developer team. They hated doing this. I asked them to do POSIX, and we've done a lot of POSIX, but it's not something they do enthusiastically. It's a kind of polymorphism, you could say. It's like a poor man's polymorphic interface. POSIX is great for many things. It's much better to have a standard than not to have a standard, but it's not something I would start by implementing. Or this is not where I would start. Also, you have this void pointer. Is that good C++? I don't know. I have to do some kind of typecast there. And then there's the fact that it's a pointer size interface. I've seen core guidelines, at least in some revision of the core guidelines, there was a recommendation that you should do spans instead of this. I think that, if you can have some more type-safe interface, you should. So, but whatever the case may be, however you might feel about this function signature, the fact is I have to implement that magic that's supposed to be living behind that file descriptor. That thing that makes the internet work inside your computer, that has to be implemented. And then I'm going to have to provide you with some kind of user-friendly interface on top, right? So let's look at the other system calls if there's any help. We have a lot of file system ones. That's quite a lot, It represents quite a large portion of the system calls backing newlib. And then we have these rarely needed, for our purposes, kill, single process operating system. What are you going to kill? You can only kill yourself. Yes, you're allowed to do that. We've implemented this because we have to, but doesn't really make that much sense, right? Environment variables are good for communicating small pieces of data between processes and between operating system and processes. You know, you can have them, but you know, in IncludeOS, it's much better to just go ask the operating system directly. Just fetch the values you want directly. There's one here for timekeeping that's probably useful for a web server, but it's not, you know, it doesn't take us miles ahead. And then we have these that are completely useless in a single process operating system. Fork, I can't fork, I don't know about processes. I'm one process, should I duplicate myself into two? No, it doesn't make sense. Waiting for another process also doesn't make any sense. So, let's just look at this very quickly. Why so much file system stuff and why so little networking stuff in the C standard library? My only hypothesis is that this is what the internet looked like in the 1980s. I remember this internet. I remember, except it wasn't FedEx. I never used FedEx. I had all these diskettes in my backpack, and the diskettes were taken out of backpacks and put into other backpacks, and there were, of course, never anything pirated on there, but there was definitely a lot of games on there. So that's how we exchange information. So maybe, you know, maybe that's why there's such a file system focus on the system calls. But it's not nearly enough for a web server, so we have to do more. So we actually have to implement this whole networking subsystem, and we have to do it with zero overhead because that's our mission. And we also want to, you know, alleviate the opportunities we have when we know that we actually don't have to worry about other processes getting in the way. So we have some unique opportunities to do something different. And then the question is, you know, when I implement all these subsystems, I'm a library operating system, right? So I provide, for example, if I provide a TCP object to you guys, you're making the process, I provide the TCP object. What kind, do I need like an extra set of interfaces on top? I don't know, but let's see. So let's take a small survey of the subsystems in the modern operating systems. We have memory, we have file systems, we have timekeeping, networking, parallelism, and miscellaneous. I probably forgot something, but these are at least some very important ones. And if you looked at libc, I think this is, I've used a very scientific model to derive this precise line here. You know, it roughly describes how libc, what kind of services libc provides in terms of support for or access to these operating system subsystems. So POSIX goes a lot further, and it gives you a lot more. I mean, most notably, obviously, you get the socket interface, right? So you actually get to create TCP sockets, and you get to create UDP sockets. You can send datagrams, and you can open TCP streams. That's a huge improvement, obviously. You also have pthreads, so now you can actually do threading. You know, that's nice. libc++ adds a lot of value on top of that. Again, in terms of memory, we have STL, we have stud file system. I think that's just recently gotten approved, has it? So that's great. We have stud chrono. That's much better abstractions for timekeeping. And then there's a networking TS that I'm hoping is going to turn out great. It's not there yet, but of course, in terms of concurrency, there's a lot of work, a lot of additions C++ has been doing as well stud thread, async, coroutines, etc. So still some things might be missing. I'm always interested in the low-level stuff. You know, might just be me, but I'm a systems programmer. I think many of you guys are as well. So when we talk to people, we see a lot of people trying to get the Linux kernel out of the way and trying to kind of get through this opaque barrier of system calls without going through the whole hassle of, you know, modifying the Linux kernel and writing kernel modules. That's quite hard. So, you know, having some very clean, low-level interfaces, you know, I thought that would be interesting. And obviously, HTTP is missing, you know, so we contribute with our squiggly line. It's not any straighter, it's not a much cleaner line if you try to express it as a line, but we have a lot more going on the networking side because we actually implemented the whole subsystem. Obviously, that's not the job of the C++ standard library, at least I don't perceive it to be, but you know, we had to do it for our purposes. So we have added some stuff, but instead of considering this a line, I just want to talk about how we are doing it. We're just implementing all these well-defined subsystems as C++ classes. So it seems a bit artificial to draw this kind of absolute line, this distinction between, this barrier between operating system and user space. It seems a bit artificial, at least in our context. So we're implementing all these subsystems, we're providing a lot of high-level abstractions, and we're also implementing objects for the low level. So people might be missing this very clean boundary. I don't know if you guys are, but it's of course an important question for me to ask myself when I'm saying that I don't really, I don't want to shout hooray for the POSIX standard, even though I see its importance, so some people might, complain and they might want these clean layers. So we've been thinking about that and trying to figure out where should those clean boundaries be. This is one place to draw the line. If you want to address web developers, this is one way to do it, to just say, let's just provide some really clean HTTP interfaces. Because obviously, if you have an IP stack in TCP, well, you're going to want HTTP and that's all. Yeah, that's true for web developers, some web developers, but it's certainly not true for systems developers. So you want something more? Okay, so you can get access to TCP connections or part of the TCP connections through these opaque file descriptors that they're just magic numbers that, I don't know. POSIX provides some of that. You also have this other less clean interface. POSIX also includes a whole set of tools. It's standardized, actually, a lot of these command line tools, which to get all together forms kind of an unholy mess, a way to access all the parts of the systems, but at least, yes, it's very useful, and that's just how things evolved, I guess. So, but if you want, a clean access to everything, I don't know a simple way. So we're trying to make that happen. So some of this comes from, some of these layering issues, it comes from the protection boundary, right? And it makes a lot of sense. Let me stress that. It makes a lot of sense. It's absolutely no way to make a general purpose operating system without having this protection boundary. Obviously, you can't have one process here, you have Microsoft Word here and Google Chrome here, overwriting each other's memory. It's just not possible. You can't have it like that. So for that reason, you have these protection boundaries, but once you don't need those anymore, it opens up the space of opportunities. So that's just a look inside to be more concrete. These are some of the classes we've implemented. We have the network interface card, we have Ethernet, we have TCP controller, we have ICMP, we have TCP connections. For each of these protocol handlers, we have implemented packets as simple, clean C++ classes, so you can actually get the actual IP4 packet and you can access the members of that packet through a normal C++ interface. So that's just what we did, and then POSIX. Obviously, we want this operating system to be useful. We want it to be able to support legacy code. So we're making a POSIX compatibility layer on top of there. But it introduces some strange and unnecessary abstractions, the first of which is blocking, because our operating system is async by default. We've used the simplest possible form of async programming, which is the leanest and smallest way, and that's callbacks. You can build a lot of abstractions on top of that. That's not the only paradigm we support. You can use Boost ASIO on top as well. But having to put this POSIX compatibility layer on top, it forces us to support blocking. Okay, so we need to support context switches in order to have that. It's not efficient, but we need to have that for this legacy interface. I say make your own layers. We already have these C++ objects, which are small APIs in their own right, representing well-defined objects. We didn't look at the POSIX standard, or we didn't primarily look at Linux when we implemented this. We went to the source, the RFCs. IETF, it's the standardizing body for the whole internet. They have really well-written standards for all these protocols. So we went directly there and implemented using modern C++. So the result is that we have all these quite well-defined, they're getting more and more useful. We're actually using them to deploy software now, and And you know, I think that's in my mind what I need in my job. I don't know what you need, but I don't need POSIX, but we're implementing it. So obviously, we want to also stay synchronized with the standard library. So there's a networking specification. I think it's scheduled for C++ 20. It looks like it's going to be working on top of POSIX. So that means you'll have a rich set of C++ abstractions from the standard on top of this opaque POSIX layer. And if you have this running on top of IncludeOS, you know, that's modern C++ on top of ancient C on top of modern C++. It seems unfortunate, so I hope we don't get there, although it might seem unreasonable to have the stud network conform to the IncludeOS IP stack. I mean, maybe sometime in the future. Might seem unreasonable, but I think Bjarne Strøstrup said today that all progress depends on the unreasonable man. This is a quote from George Bernard Shaw, so, you know, who knows? I'm not giving up. So anyways, I thought I was done with these layers until I got this email from Dan and Ricardo at IBM Research. So they were running IncludeOS on top, and they were running the demo application we showed last year, which is a lot of HTTP abstractions for making RESTful APIs. And they were running this application on top of their new, very, I would say, avant-garde kind of hypervisor. And very cool is that they reduced our boot time from 300 milliseconds to 10 milliseconds. I thought 300 milliseconds was quite good, you know, but you know, 10 milliseconds is much better. So let's look at that. So we have all these squiggly lines, and this is where Solo 5 comes in, right? That's actually a pretty straight line. And I'll validate this straight line by actually looking at their code. So this is the interface. This is the low-level hardware interface that these guys have defined, and it's sufficient to run this very rich modern C++ application on top. So they have network packet read, network packet write. Well, that sounds very intuitive. I understand immediately what that means. Block device read, block device write. Right? So read a single block, write a single block. That's something you would put below a file system. But it would also make it easier for you to figure out how to make your own file system or to experiment with different types of file systems. And then you have fast console output. Obviously you want output. Okay, that sounds very nice and reasonable. And you have two types of clock, monotonic clock and wall clock. Sounds like all you need. And then you have this very interesting one that actually replaces all of our IRQ handling and all of the timers bundled into one single call. It's called poll, and it says sleep n number of nanoseconds, or sleep until n number of nanoseconds have passed, or until there was some I/O. So our whole event loop, instead of waiting for interrupts, we're just doing this call. So we're looking at our timers and we're saying, okay, so no timers have expired yet. When is the first timer that's going to expire? The first timer that we have registered is going to be expiring in n nanoseconds. Okay, so I pass that number to this call here, and that call is going to wake me up when a timer has occurred or when there has been some I/O. So it replaces pretty much all of this. Now, it's not true that it replaces it, because Solo 5 is just an interface. But, you know, just to get an event loop running and to get timers running, we had to implement a whole lot of stuff on x86. You can look at that code, it's a lot, and this is not even all of it. This guy. You notice blocking calls. Yes, that's true. There are blocking calls in the Solo 5 interface. And so this is one of the tricky side effects, number 4. I'm not going to go into detail about it, but once you want DMA to happen, what does that mean? It means that you have a device that's supposed to put data into your memory, and then you're going to, and then once it's put data into your memory, it's going to interrupt you, right? And you know, you could start thinking, how should such an interface look like, a shared data structure like that? You could say, okay, let's just have them all in an ordered array. So I have a continuous array of network packets. Well, that's great, but you know, how about fragmentation? Do you think network packets are always going to just line up like that, then it's a lot of copying, right? So in order to avoid copying, etc., you need some sophisticated data structure, and it's quite hard to test, etc. This is something tricky with DMA. Zero overhead solution, I still think it is to have DMA, but it's surprising how much you were able to do with Solo 5. So it works like this. This is just how the layer enters. So Mirage, that's another unikernel project from Cambridge, acquired by Docker, those guys. So they use Solo 5 as an overlay on top of their drivers for running on KVM. So that's when we're running in full hardware virtualization. They use this simple Solo 5 interface to get their application and the rest of their operating system running on top of there. The IP stack, etc., is all running on there. So that means inside the virtual machine, they have a set of drivers that again will implement this Solo 5 interface, and it's all inside the virtual machine. Another way to run it, which is how they had implemented it for us, is that they actually put the devices. They don't put the devices inside the virtual machine. So that means they provide a network driver for IncludeOS, which just does a trapping call whenever it wants to fetch a network packet. So, and this adds a lot more protection. So, it's hard to visualize all this stuff. I hope you can, it's probably hard to follow, but what's happening here is that the Solo 5 interface is the bottom layer, and below Solo 5 we don't have any network drivers that we have implemented ourselves. We just have these trapping calls. So essentially the work of the driver has been moved down to the host. So the host is going to be in charge of moving network packets in and out. So it adds a lot of flexibility, and also they give us some security, some real cool security guarantees. When you run IncludeOS in Solo 5, it's actually going to do memory protection of the ELF binary, because we provide an ELF binary. In that ELF binary there are segments with different protection flags on them. So with Solo 5 they will actually load that and set the protection inside of the virtual machine memory from the layer below, so that we inside of IncludeOS can't change it. And that gives you absolute protection if that's what you guys want. So that means you can actually have a guarantee that says you can not write to the same memory that you can execute. So that means you have a strong guarantee. Inside of IncludeOS, there is no way that I can receive data, write it into memory, and then jump to that memory. It has some interesting side effects. For example, we're doing something called live update. That's not going to work. We have live update where you can receive a new version of the IncludeOS binary. You can actually replace yourself, so you can replace the whole contents of the virtual machine in 5 milliseconds or 10 milliseconds or something. It's really fast and it's really neat. That's not going to work there. So there's still some interesting work in figuring out exactly where this balance should be struck between security and the ability to update, etc. This could also obviously be used as a hardware interface on bare metal as well. I want to give a shout out to Bearflank. This Ryan Quinn is here today. They're taking an even more radical approach. So they're actually, tossing KVM aside. So Solo 5, they use an interface to KVM, which is a kernel module in Linux, in order to run the virtual machines. Bearflank, they're actually implementing all of this from scratch for both Windows and Linux. I still don't know exactly how these interfaces between guest and host are going to look, but I'm sure is it somewhere along these lines? Yeah. So I'm really excited about that project as well. This is pure C++. It's really well tested, so go see Ryan Quinn's talk and then check out that work as well. So approaching the end here, we're seeing that we're making an ecosystem. We're implementing all these protocol objects. These subsystems in C++ already. It doesn't seem like we really need this neat POSIX layer on top, but it looks like it's possible to make some very neat layers on the lower levels. So we have a guideline for POSIX. We want to implement the modern C++ variant first, and then we do this optional POSIX layer on top. So there are no perfect layers. So how much should we allow the user access to? And I think the answer is everything. Would you agree? Can you tell me one thing inside the operating system or inside the hardware that you want me to restrict access to? Something you absolutely certain that you never want access to? I think the general answer has to be, I want to be able to access everything. So we want to give you access to everything, but we don't want you to get everything at once. We don't want you to pay for the parts that you don't need. So unless you explicitly ask for it, it's not going to get included into the final binary. You also said today, Strostrup, that you should make a connection with hardware. It's abstractions all the way down. And I agree. Unfortunately, some of these abstractions are very opaque. So if you go, if you just start trying to interface with Linux, you're going to see that you'll reach the level of the system calls, and below, it's just a black box, really. Obviously, it's open source, which is great. You can go in there, rebuild Linux, make your own kernel modules, but we are trying to make an environment where you, as a C++ programmer, already has access to all these subsystems directly. So we're trying to answer all these questions. How do I boot my HelloWorld program? We answered that today. How do I boot my custom kernel? We have tooling for that so that you can start implementing your own kernel and say boot dot and then boot that kernel code and start working. Boot a web server, C++ web service with modern abstractions that we showed last year. We're working on routers and firewalls and load balancers. So these are systems where you typically need part of an IP stack and not the whole IP stack. So it makes a lot of sense for us to have a modular IP stack where you don't just get this huge box or nothing, you can pick and choose the components you want. So the green ones are available now. Firewall, routing, load balancer, those are in the works. Our CEO actually reported 13% faster, that we were 13% faster than Linux when we were routing a ping flood. So we're very good on latency, it seems. 13% faster, that's pretty cool. Yeah, so he wants me to boot that web server. I've been talking about it. So this is how it looks. I'm not going to have time to go into details. There is a talk tomorrow where I'll cover more of that, but this is how it looks, and you might notice that we're making a unique pointer here to something just called a HTTP server. But what I think is interesting is that this is just one of several abstractions we have available. We have, if you want just to have an example where you run TCP and write text directly to TCP, you can do that. This is an abstraction for HTTP. And what I think is interesting is that you build that HTTP server object on top of a very transparent set of subsystems. So we have an IP stack that you can access, and you can grab hold of the TCP part of that IP stack, and then on top of that TCP part of that particular IP stack, because you can have many, so on top of that you attach your web server. You can see already that we are, this is our callback. This is a way to do callbacks. So on request, and we're transmitting a lambda in there. So whenever there's an HTTP request coming in, this lambda is going to be executed. That's not the optimal way of using this callback system, but it's very efficient. But when you use delegates and add delegates into the equation, which I'm going to show you tomorrow, then it gets much easier to work with. So you can boot it. Now it has networking. So if you boot something with networking and you want it to be able to talk to the surrounding environment, you say create bridge. So we'll set up a bridge for you so that virtual machine will come up and it'll have kind of a virtual wire connected to a virtual bridge so that you can talk to it. It boots something like this, and then you go to the web browser and you go to that IP address, and hopefully you see that web page. So, how am I on time? I actually have gone a little bit faster than I thought. But so tomorrow I'm going to cover this code in more detail. I never thought I'd get to the end of these slides, but here we are. So I'll introduce you to modern C++ delegates and how we wire all these C++ objects that I've talked so much about, how we wire them using delegates. That's a quite interesting technique, and I'll show you much more code examples. How to do fast DMA zero-copy IP stack with tens of thousands of concurrent connections and zero context switches on a single CPU. That's a true statement. We're doing that. We're not doing any context switches, but still we are getting a lot of performance for a lot of concurrent connections. And the reason for that is that we have a very, very slim and minimal sort of event loop that drives the whole thing. So we're going to talk about delegates, how they make the zero overhead async programming easier. You can also build other stuff on top of that. I mentioned Boost ASIO. That's also something. It has a flexible backend so that you can make a IncludeOS backend for it. So there are alternatives. But of course, we're also going to point out some tricky issues. It's not just easy. So yeah, we'll look at those, and there are reasons for wanting coroutines, channels, multi-core abstractions. We do have multiple cores in IncludeOS, and we do have a way for you to assign a function to an actual core. That's going to be a separate talk on Meeting C++ in Germany. Conclusions: operating system, subsystems don't have to be sub anymore. You can get access to all of them. Some unusual side effects you have to consider when you're programming for the operating system, but the resulting environment that we provide is something where you'll feel like you're just programming normal C++, but you actually are in full control. POSIX isn't bad, but I think it's bad C++. It also has some costly side effects, so that's one reason why I don't think that's a perfect operating system abstraction anymore. I'm not saying we should throw it out the window, by all means, but it's not the perfect abstraction. It's not suitable for our purposes. So, that's it actually. Come find us. If you have any questions, I guess we have time. Yeah? For ARM, oh, that's a good question. Well, one of the things we have done recently is, or actually within the last year, we switched from 32-bit to 64-bit, and when we did, we tried to keep support for 32-bit. So that means if you go into the source directory, it's all open source and available on GitHub, you'll already see that we have done a lot of work in terms of separating architecture-specific stuff into separate places, and the build system is integrated with that so that you can kind of specify which architecture you want to build for, and it will produce a binary corresponding to that. We have been running a lot of our tests, and I think the IP stack has been run on ARM. But you know, the subsystem, the driver layer, that's not implemented for ARM. We are moving into running on bare metal. We've done successful tests running on x86 bare metal. That was quite exciting, and ARM is obviously the natural next choice, but I can't give you a particular date. Any other questions? No? Okay. Come find us. Go to the talks mentioned here.